So far we've been talking about Newton's second law sort of implicitly, and we've been writing F equals ma, right? Force is equals mass times acceleration. And that applies in a lot of cases, but it's actually not really quite right. Really, if you go back and you dig through things a bit, what actually Newton wrote was F is d by dt of mass times velocity, or another way of writing that is that the force tells you what the time rate of change of the momentum of an object is. Now, it seems like that's not really a big distinction, right? If you look at this, F equals ma, well, if I take a derivative here, then the derivative of the velocity is the acceleration, so this does give me F equals ma, but it's a distinction that ends up being important in a number of cases. It can be important, so it's an important distinction. First of all, when masses are changing, right? And the second case in which it's an important distinction is actually when you're dealing with multi-particle systems. Because it makes sense to talk about what the acceleration of a single particle is. It doesn't make quite as much sense to talk about what the acceleration of a collection of particles are, although there's certainly ways that we can do that. And so introducing the idea that force is not given, doesn't tell you what the mass times the acceleration is, but instead tells you what the time rate of change of the momentum is, ends up being pretty important. Now, in order to get there, we first have to just ask the question, what is momentum? And I'm going to give one of those really inadequate answers to that question. Momentum is defined as, so the momentum of a particle is defined simply as the mass of the particle times the velocity of the particle. So that's how we write the momentum of the particle. It is a quantity that's associated with the particle. It turns out to be a pretty fundamental quantity for a particle. It's important in a lot of contexts, and particularly important in that it's related to force. But it just is. That's definitionally what the momentum of a particle is. But we can also write what the momentum of a system of particles is. So if we imagine we have some system, right, there are a bunch of particles that are all moving in different directions. So this is maybe particle 1, 2, 3, 4, 5. You can also talk about what the momentum of this system is, right? So I'll draw a system boundary around that, and the momentum of the system is simply the sum of the momentums of every particle in the system. So I'll write a summation here from 1 to 5 in this particular case, since there are 5 particles here. The total momentum of the system is the sum of the momenta of each particle inside the system, and of course I could write that out more explicitly as the mass of the ith particle times the velocity of the ith particle, summing from I equals 1 to 5 in this case, or in general if there are n particles in the system, summing from 1 to n. So that's how we talk about momentum for a system of particles. And finally, we can imagine talking about what the momentum is for some extended object. So instead of thinking about a system of particles, let's instead think about some asteroid, right? The asteroid is flying through space, but it's also spinning around. And so as that asteroid moves and spins, how do we think about what the momentum of that asteroid is? Well, just as here in this case, we thought about a system that consisted of a bunch of particles, in this case, we could also think about the asteroid and basically break the asteroid up into little chunks, right? And ask the question, what's the momentum of each chunk inside the asteroid? And so we might initially sort of think about that again as being a set of chunks. Or more equivalently, more strictly, if we thought about this as a continuum, we would actually want to integrate over the entire continuum. So we basically go to each point in this asteroid and we ask the question, how much differential bit of mass is there here? So there's some differential bit of mass, dm, and also what's the velocity of this point? And when we ask that question, we can add those all up. So sort of notationally, we'd say the momentum is the integral over the object of the velocity at some position in the object times the differential mass located at that position in the object. Okay. Now at this point, you don't necessarily have all the mathematical tools that you need to be able to do this, so I just want to highlight instead the conceptual idea. All we're doing here is basically taking every single little chunk of the object and asking the question, what's the momentum of that chunk? So this integral is basically imagining that we're going to each little bit of mass in the object, and we're asking the question, how fast is it moving, and how much is located there?